Hi, everyone. Hey, hi, everyone. I'll just share my screen so I can start my talk. Can everyone see that? I'll take nods as a yes.
Yep,
awesome.
thank you.
So
it's not full screen, Rose, if you wanted to put it in full screen.
Sorry, it's not full screen.
If you wanted it in full screen, it's not at the moment.
Ah, okay. It's full screen on my computer. Oh, it's saying sharing is being paused. So let's try. Resume share. Is that working now?
Thank
Okay,
you.
that looks good.
Cool. Okay, so this area of mathematics is it's not exactly what I'm doing now. I'm working in a similar area, but it's probably one of the areas that inspired me to pursue mathematics, both in my education and my work. Yeah, I basically got really interested in chaos theory and how it related to climate science, particularly now that climate science is having such an impact on basically our futures. So yeah, that's kind of like the background of why I was inspired to give this particular talk, even though it's not exactly the area that I'm working on at the moment. The area that I'm working on at the moment is more to do with looking at different climate scenarios and their impact on the Great Barrier Reef. But yeah, here I am to talk about noise-induced tipping in geophysical systems. When I talk about a geophysical system, I mean systems like the climate, the oceans, the atmosphere, these kind of large-scale dynamical systems that make our Earth go round. And this talk is based loosely on a workshop I did while I was doing some study in the US. It was a workshop funded by the Mathematics and Climate Research Network and the National Science Foundation. And it was by Professor Mary Silver from the University of Chicago and Dr. John Gamma from the University of North Carolina. I just feel like I should acknowledge their input. So first of all, I'll talk a little bit about tipping points all around us. So some tipping points from the past and predictions for tipping points in the future, just to give you an idea of the sort of tipping points I'm talking about. Then we'll kind of dive into some definitions of tipping and equilibrium bifurcation theory. So that's the kind of mathematics behind tipping. This will kind of lead into some more complicated examples of tipping mathematics, like bifurcations with hysteresis. And then we'll talk about noise-induced tipping and how we can use a very simple model to understand tipping in climate or a geophysical system. And then I'll finish by talking about some research in tipping, just some research that I think is kind of cool and helps you understand some aspects of different aspects of Earth systems. So first of all, some examples from the past of tipping or that have been speculated to have occurred in the past. Green Sahara is one example. So it's speculated that where the Sahara is used to be green, and at some point millions of years ago, we tipped into the desert state that the Sahara is in now. So that's one example of a tipping point. Greenhouse versus icehouse Earth. So this is a tipping point, which is again speculated to occur every many million years. So it's got a very long time frame in between tippings, but basically it's this tipping in between a very hot, moist Earth and a very dry, icy Earth, and it's believed to be to occur due to volcanic and tectonic activity. Another example is snowball Earth, which is this kind of hypothesis that at some point earlier than 65 million years ago, the Earth was covered in ice. So very different from the way the world is now. So these are all examples of tipping points that are speculated from, for example, paleoclimate data. Then there are all these tipping points that are predicted to occur due to climate change. It's a little bit depressing to look at some of them, but and of course, all of these are speculative, so we're not really sure because tipping points into the future are a whole lot harder to predict. But some of the tipping points that are possible are the sudden decay of the Greenland ice sheet. So it's speculated that we could see this sudden change in the rate at which the ice sheet is decaying. Collapse of the thermohaline circulation. So the thermohaline circulation is this oceanic circulation, which is extremely important. It occurs due to temperature and salt gradients in the ocean. And so it's speculated that this could collapse due to warming. Changes in El Nino. So you've probably heard of the El Nino oscillation, which has a huge impact on hydroclimate. So that there's speculation that we could see changes in El Nino modes. So El Nino, as I'll talk about later, it has a kind of a weak mode and a strong mode. And so there's speculation that these, how these modes change could, be tipped into a different equilibrium. Other examples, Amazon dieback, Sahara greening. So we could go back to that green Sahara that's predicted to have happened millions of years ago. So there's all these different changes that could occur due to tipping points in different Earth systems. So now that we've gone over some kind of solid examples, I'd like to introduce some definitions that are thrown around in this area. So I thought I'd start with the kind of policy definitions. So the Intergovernmental Panel on Climate Change, which is really well known for producing those reports on the state of the climate. They describe tipping as an irreversible change in the climate system or an abrupt change to the climate system that could be reversible. So that's kind of a nice solid definition. The math definition is a bit more like very wordy, as math definitions tend to be. And it's any system that bifurcates with hysteresis. So we'll unpack that later. But basically noise-induced tipping, which is what I'll talk about eventually, is caused by noise from outside of the system, which basically means it's noise that's unaccounted for in the model. And this is very common in climate systems because the climate is a completely open system. Well, completely open is a debatable way to say it, but basically there are so many things that we don't account for in our models because it's just so complicated. And so noise is basically always going to be there. I'm not sure why that happened. Okay, cool. So what we're going to do to start to understand this mathematical definition is go through a really simple example that you might have seen in some first year mathematics topics, potentially second year mathematics topics. And it's basically called a stability analysis. So you look at your differential equation. So x dot is just the change in x with respect to time. And instead of just analyzing the system like we normally would, where we run it over time and see what its behavior is like, we consider the behavior of the system according to its parameter mu. So here I've got the system plotted for different values of mu. So you can see that depending on the value of mu, we have a different number of intersections with the x-axis. And this is important because we're interested in when in the roots of this system. So you can see that when mu is less than 0, we have no intersections with the x-axis. When it's equal to 0, we have 1. And when it's greater than 0, we have 2. So there's this point here at which the number of intersections changes, which we'll eventually call a bifurcation. So as I said, we can talk about the number of roots it has at different points in mu. And what this does is it creates what we call a saddle node type bifurcation. There's lots of different types of bifurcation, but this is one of the kind of classic bifurcations that you tend to look at in bifurcation theory. And we get this by plotting our fixed point. So that's where the system is equal to 0, or our intersections, against the parameter mu. And so what you get is what we call a stable branch and an unstable branch. And basically what that means is that for the stable branch, your system will tend to move towards your fixed point. And when you're on your unstable branch, your system will tend to move away from your fixed point. That's a very simplistic description, but that's basically what it means. It means you're either going towards equilibrium or you're going to move away from equilibrium. And so your stability is implied by the value of f dash. This isn't quite right. It's actually implied by the value of f dash near x star, not at x star, because of course that'll be 0. And this kind of analysis gets a lot more complicated for nonlinear and high dimensional systems. You have to use stuff like Lyapunov exponents, but it's quite easy for systems like this, which is why they're great examples. So after looking at that nice little example, we're going to look at a slightly more complicated example. And this is a nice a nice model of Earth's temperature balance. It looks kind of complicated, but it's quite simple for a geophysical model. And so what we're interested in here is big T on d little t, so it's the change in temperature over time. And it's modeled by the difference of the energy flux in and the energy flux out of Earth. Very simplified. We have alpha, which is Earth's albedo, as a function of temperature. We've got all of these non-dimensionalized constants that I won't go over. If you've done some calculus, you'll know that we often non-dimensionalize just to look at parameters that are important to us. Sorry. And then we have emissivity. And emissivity is quite related to albedo. It's the ratio of energy that's radiated from a material surface relative to a black body. And a black body is like a perfect absorber. It absorbs everything. So it's kind of a measure of how much you're reflecting versus how much you're absorbing. Then we have T star, which is the equilibrium temperature. And we have some other sort of constants for the ice and ocean albedo. So it looks really complicated, but what we're really interested in is the emissivity, because that gives us some sort of measure of how much energy is being absorbed or reflected. And what we're going to do is do this simplification in order to solve it nicely, where we say that epsilon is slowly time varying. And this is actually not a bad approximation in certain scenarios. So when we do that, we can plot T star against epsilon like we did with our other parameter mu, and we get what is called a fold bifurcation. And this sort of system follows what we call a hysteresis loop. So we can use this system to show something similar to tipping between snowball Earth and hothouse Earth. So basically, the upper branch and lower branch are our stable branches, and we have an unstable branch in between. So that means we're going to tend to hop from stable branch to stable branch, because if you remember, we tend to not stay on our unstable, on the points along our unstable branch because it's unstable. So you can imagine if you had a really low equilibrium temperature down on this branch, and you slowly decrease the emissivity, then you slowly move up this branch until you got to this kind of key temperature, then you're going to suddenly hop up onto the higher branch. So that's a bifurcation. Conversely, if you started on the upper branch at a really high equilibrium temperature and then slowly increase the emissivity, you're going to suddenly jump down to a really low equilibrium temperature. So this is kind of like if you imagine the lower branch as snowball Earth, because it's lower equilibrium temperatures, and the upper branch as like a hothouse Earth scenario. So this is like a really simplistic model of Earth's heat balance, but it kind of helps us to understand a type of tipping point that the Earth could go through. And these sort of diagrams, not this particular one, but they're often associated with climate feedback loops. So you can imagine this kind of system, but where you have a positive feedback. So one that continues to increase your equilibrium temperature. And so that's the kind of feedback that we are potentially going through at the moment with some of our positive climate feedbacks. So we've looked at a really nice simplistic model, and there are a lot of nice simplistic models out there. And so they seem kind of stupid because they're so simplistic, but I just want to emphasize the kind of importance of these models. So there are a lot of these models out there, and although they're very simplistic, they help us mathematically explore some extreme situations. So a really famous example of this is a model that was created called Daisy World. And so Daisy World was this computer program. It was created quite a while ago. So it was basically just like, it was coded very simplistically for the time. But it's this really nice model where you have perfect sphere, and you have white daisies and black daisies that you can grow on this black sphere. And so when you start the model, you kind of randomly populate your model with white daisies and black daisies, and you let them grow out according to certain rates, which are your parameters. And you can see how the reflection versus absorption of this planet evolves over time. So it's a completely unrealistic scenario, this world that's only populated by particular types of daisy. But it's a very interesting experiment in terms of the impact of albedo on climate. So what I want to say here is a lot of tipping point models are very simplified, but they can tell us quite a lot about important aspects of Earth systems. Another thing that I want to emphasize is that a lot of the systems we look at, although they may not be as simplified as Daisy World, they're always going to miss out something. And so because Earth systems are not closed, and so realistically, we should always include some form of noise in our models that represents what we're not accounting for. So now I'm going to start talking about noise-induced tipping points, because we want to start including noise in our models. So I'm going to talk about this very, very important model for atmospheric convection. It's a very famous model called the Lorentz Model. You may have heard of it potentially if you've done a DE's course, because it's very famous. And it's famous because it was used a lot in the discovery of chaos theory. So it kind of has this crucial role in the discovery of that area. But it's a very simple model. It basically models the atmosphere as fluid that's heated uniformly from below and cooled uniformly from above. So there's a lot that it's missing out, but it's really cool. It's a really cool model to explore. And if I'm allowed to, we'll see if this shares properly, but I have a little illustration of what this model looks like. So this is, I'm sorry if you can't see this very well. This is a phase space model, phase space plot of the model. So you basically plot X, Y, and Z against each other. I'll tell you what X, Y, and Z are in a second. But you, if you play around with the parameters, you can see that the phase space model is very sensitive to
Sorry, Ruth, I don't think we're able to see the screen you're
okay.
sharing.
Sorry about
Maybe try
that.
unsharing it and then sharing the new screen. Do you want to do that? I'll give that.
Yeah, try that. Sorry about that. Okay, is that
Amazing, thank
excuse
you.
my tabs?
That's okay.
Yeah, so this is what I was talking about while you couldn't see. I'm sorry about that. So this is an example of a phase space plot of the Lorentz model. It's quite famous. I think often it's called the butterfly attractor because it looks a bit like a butterfly. But you can see that as you fiddle around with these parameters, the trajectories of particles in the phase space, which is basically how particular selections of X, Y, and Z would move around in time. And you can see that they change dramatically depending on the parameters. So this system is already chaotic, much like the systems I just showed you before. It's highly dependent on the parameters in terms of how many equilibria it has. So these points here are kind of like equilibria. in that trajectories tend to orbit around them. It's a different type of equilibrium, but it's very similar to the fixed points we were looking at before. But yeah, the number of these points varies depending on how we play around with these parameters. So now that I've shown you that kind of acontextually, that I'll sort of give you more of an overview of what the model actually means. So I'll stop sharing and then share my other screen. Yeah, so now we've got an idea for what that model looks like in phase space. I'll just go through what the variables in the model mean. So X is kind of proportional to the rate of convection, Y is the horizontal temperature variation, and Z is the vertical temperature variation. You have these other parameters, psi, rho, and beta, and they mean various things that I won't go through, but they're kind of parameters, so they're constant for a particular scenario. So that's the kind of non-stochastic model. Then what I've done is I've added this stochastic component. So sigma 1, sigma 2, and sigma 3 represent noise in the X, Y, and Z coordinates. So what you can do is model this as a stochastic differential equation to see how it moves through time. Yeah, and so the strange attractor is what I was showing you before, and it's a particular type of phase space model. So we're going to model it as a stochastic differential equation. So here are some plots I've made up for different parameter combinations for the same model. So this one here, rho equal to 13, beta equal to 2.7, and psi equal to 5 is a very common combination of these parameters because it represents a particular type of convection scenario. But this time I've run the model as just a regular deterministic model because sigma 1, sigma 2, and sigma 3 equal to 0. And you can see that when I do that, I get a single point about which trajectories rotate. So they slowly in time tend towards this point in the phase space, but it's just one point. Conversely, over here, I've got exactly the same combination of rho, beta, and psi, but I've decided to add noise in the X direction. So sigma 2 is equal to 1. And you can see that with that little bit of added noise, suddenly I have two obvious kind of fixed points that these trajectories in phase space are rotating around. And there's actually also another one right here, which is unstable. So trajectories tend to swing by it and then swing back into this and around. So there's actually 3 points here now, whereas here we only had one. So again, a really simplistic system, but it helps us understand how noise in our system can induce an entirely different array of fixed points. So we have a whole different selection of potential equilibria that we could reach. So just to finish off, I'm going to talk very briefly about some cool research in this area. So tipping point theory isn't just looked at in climate science, it's looked at in a lot of different areas. One of those areas which is of a lot of interest is pattern formation in vegetation. And the reason for that is that theory has suggested that there's a particular sequence of patterns in vegetation that occur, which suggests that vegetation collapse is going to happen. So you tend to see a particular sequence of patterns before you get desertification. And predicting desertification is important because it has all sorts of implications for agriculture and that kind of thing. Yeah, so what's been found is you get this particular sequence, but it's also been found that this sequence breaks down in many scenarios. And what researchers have found is that the scenarios in which the sequence breakdown is due to non-linearities. So non-linearities are very similar to noise. So when you have systems that have noise in them, the sort of sequence of equilibria changes. So that's another kind of area in which they've realized that noise-induced tipping points occur. So that's a really cool sort of application of the theory. Another application is El Nino mode tipping. So I talked briefly about this when I was talking about some examples of tipping points. So it's really important for us to be able to predict the strength of El Nino, or it's of a lot of interest because that has a huge impact on global hydroclimate and agriculture. And El Nino varies very irregularly between these strong and weak modes. It's a phenomenon called mixed mode oscillations. And so studies of the El Nino attractor, so it's a lot more complicated, of course, but you can look at the El Nino attractor and bifurcation. And these models suggest that weak seasonal noise can induce switching between the strong El Nino mode and the weak chaotic mode. So noise will increase due to climate change. And so this kind of means that it will probably be harder and harder to predict strong El Nino events. Yeah, so that's a very interesting application, which helps us kind of see how these tipping points could change in the future. And this diagram doesn't really mean anything, or it doesn't have to mean anything. It does mean a lot of things, but I just thought I'd include that to show how much more complicated these sort of phase-based diagrams can become when you get into these large-scale systems. So the final piece of research I'll go over is rate-induced tipping. So this is slightly different to noise-induced tipping. What researchers have found is that some tipping points can actually be induced when parameters are increased or decreased at an above threshold rate. So rather than being induced by noise in the system, all you have to do is increase one of those parameters too fast and you'll get a bifurcation. And so this kind of behavior has been found in models of the AMOC, so the Atlantic Meridional Overturning Circulation, which is this very important, huge oceanic circulation. It's very important because it helps the atmosphere absorb heat. So it's very important for the Earth's kind of natural mechanism of helping to stabilize temperature changes. And basically, tipping points of the AMOC have been shown to be dependent on freshwater forcing. So that's the kind of amount of fresh water that's running into the ocean. And researchers are really interested in rate-induced tipping thresholds for the AMOC because it will help them predict the sort of rate at which you need to increase those parameters to induce AMOC collapse. And we want to avoid that. So it'll help us put some sort of thresholds in policy and that kind of thing. So again, some kind of complicated diagrams, but just showing how when you get these more complicated systems, you're often not looking at one phase space, you're looking at many many sort of plots of different parameters against each other to try and put together a sort of high dimensional image of this bifurcation. So that's the research that I thought I'd share with you. There's a lot more out there. There's recently been a lot of interest in early warning events, which are basically behavior that occurs before a tipping point that kind of suggests that it's going to happen, because obviously that's of interest because then we can kind of look at these warning signs and try and make changes before the tipping point actually occurs. So that's another really interesting area of tipping point science. So in summary, we can think of tipping points mathematically in terms of bifurcations and hysteresis. Tipping points are very relevant to explaining a lot of past and future phenomena in Earth systems, as I went through at the start of the talk. Noise-induced tipping is caused by noise from outside of the system, and that's not necessarily some sort of erratic behavior, it's just behavior that's not accounted for in your model. And current research includes explaining pattern formation in vegetation, unpredictability of El Nino strength, and rate-induced tipping in the AMOC. So there's a lot of different applications to this research. So thank you guys for listening.
Thanks so much, Rose. That was a really cool presentation. I especially love the butterfly graphs. They were really cool. And it's just so amazing to see so many concepts that I guess most of us have seen in our courses actually applied to something that's so prevalent and important in today's society. It's actually making a contribution. So thank you so much.
No problem.
everyone might want to try and give a round of applause. And everyone's got their cameras off, but maybe some support for Rose with all of her everything she presented today. Thank you so much. Would anyone like to have any questions that they want to ask Rose? So we're happy to open it up now. And if you can raise your hand if you want to ask Rose a question directly about her presentation. Anyone? Well, I'll start it off then. Rose, I was wondering, with everything you've done so far, what would you say has been one of the more profound pieces of evidence or concepts you found so far that you think is important people know about?
In terms of the research I've done, or
at the predictive modeling and like climate in general.
Okay. It's a hard one. I think something that's really hard to convey when you work in this area is how uncertainty is kind of unavoidable. So I think climate science gets a lot of flack for having predictions that have huge error bars and that kind of thing. But this kind of, as I kind of illustrated in this talk in tipping points, the chaos in these systems it just puts a bound on how much you can know about them. Because as you saw, a tiny bit of noise in your system and you can be in a completely different kind of equilibrium range. So yeah, I guess understanding how you can be using the best mathematics there is out there and still have a huge amount of uncertainty. Yeah, I think, yeah, just having a lot of respect for people working in climate science and that kind of modeling because of the difficulty of communicating, yeah, the impact of that uncertainty.
Yeah, thank you. Would anyone else like to ask any questions to Rose?
Okay, I'll let Catherine ask first.
Yeah, Catherine.
Oh, hello, can you hear me?
Yeah.
Oh, before I ask, I just wanted to say thank you so much, Rose. Your presentation was really, really cool and insightful.
Thank you.
So I just wanted to ask, so recently at the Glasgow Climate Summit, so Morrison announced that he wants to aim to reach net zero emissions by 2050. So I was just wondering, like, how do you think that will change any like predictions in the model and like what you generally think it would do for tipping points?
Sure. So it's a really hard one again because of all of the uncertainty in these models. There's been a lot of, I'm not sure how much media coverage they've got, but there's been a lot of research which has kind of suggested that various tipping points might be a bit more sensitive than we first thought. So yeah, the research is quite diverse in terms of how sensitive we think various tipping points are going to be to changes in temperature. But there will, I guess, the point that we are at now, even with the work that is being done at Glasgow, and which will hopefully yield a lot of results, is that we're kind of at a point where the train is kind of already in motion. So we probably will see at least some of these tipping points. It's hard to say exactly which ones. Most likely some of the climatic ones, hydroclimate and that kind of thing. It's really hard to say, but yeah, the way that Earth's equilibrium works, it's kind of already happened and is in the process. So yeah, the kind of policy that's being made at the moment is absolutely necessary in order to avoid kind of far worse impacts of these tipping points, but some of them could likely occur, if that makes any sense.
Yeah, it does. Thank you so much.
No problem.
Yuri, did you say you had a question?
Yeah, so when you were answering the first question, you mentioned like the best mathematics out there. Like what mathematics,
a controversial topic.
is not out there yet that we still need basically to solve these kind of problems?
Good question. I guess one of the difficulties with a lot of these systems is, as I showed you with some of these, sorry, that was the wrong way. I'm not sure how to go. Oh, there we go. Yeah, a lot of these sort of research papers that look at these very, very complicated models like the AMOC and El Nino and that kind of thing. There's a lot of kind of peeling away at various levels. So you plot two parameters against each other at a time, and you kind of try and work out what's happening on one dimension and how that would feed into another dimension and that kind of thing. And a lot of that is because of computation. It just is very computationally expensive to kind of analyze these things. So I guess one aspect is the kind of algorithms that you can develop to analyze these systems. Yeah, so making those algorithms more efficient. And I guess also the theory behind tipping points in highly nonlinear, high dimensional systems is not entirely understood. It's still an active area of research. There's kind of a lot of assumptions that go on in building these models for bifurcations and that kind of thing in these very complicated systems that they kind of say like, oh, well, we make this assumption because it's highly likely to be true without necessarily proving it, which of course in mathematics makes you squirm a little bit, but it kind of has to be done. Yeah, so there's a lot of research going into how can we kind of make the theory behind it a little bit more solid. Yeah, just because going from a very nice simple system like the one I started to one that's like very nonlinear, high dimensional, there's a lot of steps in between that. And for example, one of the classic things that you do, like you do in a lot of calculus, is you look at something very close to that point and you say, oh, we're linear very close to this point. But of course, some systems that just doesn't mean much. So there's a lot of that's kind of going on where they're trying to work out what methods work in these high dimensional, highly nonlinear systems.
It's pretty cool. Yeah. Hopefully someone will work on those.
Yeah, and I guess I guess half of it is getting more pure mathematicians into the area, because it's very much an area of a lot of engineers, a lot of scientists. Like chaos theory was started by a lot of biologists and physicists and that kind of thing. But yeah, it probably needs some pure mathematics input for some of the higher level theory.
Thanks, Ruth.
Justin asked a question in the chat. So he said, hi Rose, where did you get your data from? I remember doing a climate group project based on predicting temperature based on solar radiation, and I found it very difficult to understand data formats and use them in my code. Sure.
That's a hard one. So there's a lot of data that's available open source. So the National Oceanic and Atmospheric Association, I think that's what it stands for. You often hear it as NOAA, it's NOAA. They have a lot of open source data that you can look at, which is really cool. But a lot of the data that is studied is actually created by your own model. So you build a model, you add noise into it to generate that kind of like data error or model error. And yeah, you look at that and then maybe you'll compare it to some raw data that you've got off like an open source site. But a lot of this kind of testing simplified models, you just build your own model and add noise to it to kind of simulate data. And you might use like a Monte Carlo method or something to try and work out whether you've got the right distribution and that kind of thing. Yeah, I hope that answers your question. Was that kind of what you were asking, or?
Justin, I mean, he types it in the chat, so maybe he's not able to respond.
Yeah,
but, sure. Otherwise, Andrew has a question as well. Andrew?
Yeah, so thanks, Rose, for that. Oh, okay. Justin actually asked another question. So, okay, it's maybe you want to answer Justin's question first because it's a quick follow-up.
Sure.
Yeah.
Oh, sorry. Yeah, Justin, he said, do you need to understand IRL data though? Because how do you simulate data?
Yeah, so often data assimilation is a pretty common method for these models. So how data assimilation works is you have your model, you have added noise to it, which kind of simulates error in your model, and then you have data, which you assume the noise has a particular type of distribution, and you can kind of correct your model according to the difference in your data and your model at particular points in time. But yeah, that requires you to build your model first, and then you can kind of build a data assimilation model for it. And how do you know you have the right distribution? You don't really. That's one of the kind of key uncertainties about this system, because what you tend to do is you say like, oh, Gaussian noise is really nice to model with because it has all these nice properties. Let's add Gaussian noise. So there are a lot of researchers who are looking at situations where, like, what if I don't have Gaussian noise? What if I have really not nice noise? What happens then? And so they look at the kind of techniques you'd need in order to manage that. Nice.
Awesome. Thank you, Andrew. Would you like to ask a question now?
Sure, thanks. First of all, very interesting talk, Rose. I think this really introduced to me the possibility of the usage of mathematics within tipping points. But I guess the question I have for you is more from a general sense, because I'm quite interested to know on how do you do your research as an applied mathematician within this area. I think initially before this talk, I had some ideas that, you'd be one of those, like you would have some data collection, like going to the fields, maybe you'd be sent all over the world, to like some extreme places. But these are all just stereotypes that people might have when we talk about climate modeling. But as an applied mathematician within this field, do you mind sharing about how you do your research?
Sure. So my research is slightly different. I'm in the decision science team at the Australian Institute of Marine Science. So we do all of the modeling to inform investment cases. And what I mean by investment cases is basically the Institute is looking at all these different strategies for interventions on the Great Barrier Reef to try and reduce the impact of climate change. So things like cloud brightening, planting, heat-resistant corals, that kind of thing. All these strategies that will help to reduce the impact of climate change on the Great Barrier Reef. So the models have an aspect of climate modeling because you kind of need to consider a whole lot of potential climate scenarios that could occur and the impact that they would have on the Great Barrier Reef. But there's also quite a bit of like economic modeling, ecological modeling to try and understand how those factors impact the reef as well. So I guess you spend a lot of time in meetings trying to understand from specialists in the field how your model should work. So I talk to a lot of ecologists, a lot of economists, and decision science people. So decision science people kind of understand how particular systems should be optimized. That's kind of like their specialty. Also talking to a lot of people who are in the field. So for example, if my model says that we need to deploy this many corals at this particular point in the reef, but I talk to a deployment person and they say, oh, we don't have boats running in that area at that time of year, it's too dangerous, then that's an obvious constraint that I have to implement in my model. So there's a lot of kind of information collection that has to happen before you can build models. The other part of my time is kind of planning models. So I spend a lot of time scribbling, trying to work out what my variables are, how to fit what I'm looking at to a particular model. And then of course coding. So I do coding in a whole lot of different languages, a little bit of MATLAB, a little bit of Python, a little bit of shell scripting, because a lot of the models we run are on the HPC, so the supercomputer. Yeah, so there's a lot of kind of collaboration to try and work out how the different parts of the project are getting put together. And then there's the kind of actual mathematics. And I guess because my work is highly applied, like there's not a huge theoretical aspect to what I do. I spend a lot of time researching the right type of model to use for the what I'm trying to achieve. So sometimes I need machine learning models. So I'll be researching like what particular machine learning model is best to fit this system, or what type of optimization algorithm should I use, or that kind of thing. So yeah, I guess you have your maths degree that gives you all of these skills, and a lot of your time is working out like which one of these skills should I apply to this particular problem. So
Thanks, Rose, for the answer. I think that was really comprehensive and also pretty interesting to hear how there are a lot of stakeholders involved in your research and how a simple meeting could impose more restrictions that you didn't even think about in the first place. Actually, I do have a follow-up question to this, to my particular question. So given my background as someone from a data science degree, yes, we have some foundations in math, but it's not probably as strong as someone like you who has taken really advanced mathematics, you've done your MPhil and all that. I'm just wondering, let's say for someone who has a semi-strong mathematics foundation, but they want to get into this kind of work here, when when you're doing a lot of like climate modeling as well as modeling ecological systems, economic systems. Like, would you say that someone like me in this case would we need to pursue a higher degree in mathematics in order to go for this kind of role, or would a bachelor's in mathematics be sufficient for this? Like, what do you think about that?
Hard one. I think it really depends on the particular company or institute that you're looking to apply for. The CEO of AIMS at the moment is really strong on getting people with a broad range of skills in their skill set. So I guess I was employed because I have mathematics and programming and all that kind of stuff, but I also have a strong background in communication and that kind of aspect. So yeah, it really depends on what your bosses are looking for, basically. Yeah, that's a hard one. And I think also teams are often made up of a broad range of skills. So we have people in our team who are more qualified than me. They've got like PhDs in climate science. So they tend to focus on a very particular part of the project, whereas I tend to do things a lot more broadly. So sometimes I'll be on the optimization side, sometimes I'll be doing some machine learning, sometimes I'll be analyzing some climate data. So I guess your skill set designates the work you do, but doesn't necessarily restrict you from your role. So I think, yeah, if your boss is like really interested in your skill set and you've got like a nice broad range of skills, then you're definitely not going to be stopped by not having a higher degree.
Awesome. That was a great answer. Just to summarize a little bit there for people in the audience who are interested, the gist is that, you just need to have the right skill set, because I guess a role within this field, it just accommodates a lot of different skill sets. So that's really great to hear. Thanks, Rose.
No problem. Thank you.
Thanks so much, Rose and Andrew, for your awesome questions. Would anyone else like to ask anything else to Rose?
I can throw another one in there while we're waiting for someone else.
Of course, thank you.
There was in the news recently. I was just quickly scouring through Twitter to find it, about how AIMS is working on something where they found the connection between the Great Barrier Reef and the growth of cancers. I came across this because it's named a couple of statisticians that I know. Do you know anything about that, and could you shed some more light on that?
I don't know much about that incident in particular, but this is like a broader issue that AIMS faces, in that we're a huge institute and the Great Barrier Reef is this very controversial, like it shouldn't be controversial, but because there are so many stakeholders, it often gets in the media. So we've been in the media for various things. Whenever we make a public statement about the reef or climate change, so we have a like huge media team that tries to control how things are sort of communicated to the media, because things go wrong and it badly impacts our ability to get funding and that kind of thing. So yeah, it's a very interesting aspect to what I do, in that like when I talk about my work, I have to be careful to some degree, because a lot of the interventions that we are looking at, they're, yeah, I guess interventions in general are seen as, they're a bit of a controversial topic because it's kind of intervening on the environment. But I guess the thing is that we've already intervened in the environment to a huge degree. So yeah, we're kind of doing what we can. But yeah, I'm not entirely sure about that particular report, but yeah, it happens quite a bit and it's quite difficult. Yeah.
So I guess slightly tangential to that point, you mentioned earlier that one of the reasons why they hired you was because of your communication ability. And I think it's, how do you demonstrate that to your future employer? Because I think it's a lot easier to demonstrate to them that you can program and you can do maths. And, how do you demonstrate that?
I think taking any opportunity you can to be in communication roles. So during my master's, I did a lot of conference talks. During my undergrad, I tried to get involved in talks as well. So I was lucky our Math Society had a they held talks that didn't have to be by like master's or PhD students. They could be by like any sort of undergraduate math student. So I took that opportunity. I was really involved in clubs. So I got quite a few opportunities to talk through that. I was president of the Women in STEM Society at one point. So that was a lot of like presenting speakers and panels and that kind of thing. So I think you just like slowly build up a kind of a portfolio of the kind of communication activities that you've done. And yeah, it eventually amounts to communication experience.
Cool, thanks.
I think Andrew has another question as well.
Yeah, so I guess I have one more question from me. It kind of relates back to the advice that you're giving on, how you build up your communication skills. But I guess my question now is, if you were to give advice to someone who wants to tread in your path, Rose, so someone who wants to do master's in maths, or maybe just anyone in general with a mathematical degree wanting to get into the career that you're sort of in right now, what's the advice that you would give them?
I think to not kind of restrict yourself with ideas about what you should be doing, because I think like most of my degree, most of my working life, I've kind of taken opportunities as they come to me. And I think often there's this point before you take an opportunity where you kind of think like, oh, is this in my game plan? Is this the right thing for my persona kind of thing? But I think you make your job what it is, or your study path what it is, because you will have an impact on what it becomes. And so it's not like they're trying to fit you into a box or something. So I think it's really important to occasionally take opportunities that don't exactly seem precisely what you want, because often you won't get exactly what you want, because the world is a constrained system. You're not always going to get exactly what you want immediately. People talk a lot about ladders and building up your CV and that kind of thing, and I think it's a lot the same for opportunities. Yeah, and I guess another aspect is it's very common in mathematics, and particularly if you're a minority in mathematics, to get a lot of self-doubt and to maybe turn down opportunities because of imposter syndrome, or thinking you're not qualified enough for something, or like maybe not even applying for it because you don't feel qualified enough. But I think like it's really important to realize that no one's watching. You might as well apply and just see how it goes, because a lot of the opportunities I've got, I kind of thought I wouldn't get them, and then I did. So yeah, it's important just to try it out.
Awesome advice, Rose. Thanks so much for that.
No problem.
Thanks, Rose, and everyone for your questions. Does anyone have any final ones before we wrap up this event today? If not, just a big thank you again to Rose for presenting today. It was so amazing to hear your talk. And again, it's just so great to hear how we can apply what we're doing to something so much bigger. It's amazing. So thank you so much for presenting and taking the time out of, I'm sure you're very busy scheduled to come talk to all of us and come back to UNSW for a bit, even if it's online. And thank you everyone for coming. I think that will conclude today's event. Thanks.
Thanks again, Rose.
Thank you.